A very good morning to you all. So, we are back again. I am sure you all are eager to know some more aspects related to electricity and electric current. In the previous class, we have learnt about the following aspects about electricity.
A stream of electrons moving through a conductor constitutes electric current. The direction of electric current is taken opposite to the direction of flow of negative charge. The unit of electric current is ampere. To set the electrons in motion, we need a cell which generates a potential difference across its terminals. The potential difference is measured in volts.
Today, we shall talk about the following aspects related to the electricity. What are electric charges? Types of electric charges? What are conductors and insulators? Ohm's law. In the previous classes, I am sure you have learnt about the types of electric charges. There are two types of electric charges, a positive charge and a negative charge. The flow of any one of these charges, in fact, is the flow of electric current. However, for both these charges, the direction of their motion is opposite to one another. It is also known that like charges repel each other, unlike charges they attract each other. Next, we shall see what are conductors and insulators. Let me tell you all something. There are certain substances out of all that we know which offer an easy path to the flow of electrons. These are called as conductors. And the ones which resist the flow of electrons, these are called as insulators. A conductor which offers an appreciable resistance is called as a resistor, which we will be using in our experiments. In 1827, a German physicist, George Simon Ohm, performed a series of experiments and showed that at constant temperature, the potential difference across a conductor V is directly proportional to the current I. If I is the current and V is the potential difference, V is proportional to I. Changing the proportionality to equality by adding a constant, V is equal to Ri. This constant of proportionality R is called as the resistance of the conductor. The SI unit of resistance of a conductor is ohms.
Resistance of a conductor is 1 ohm if the potential difference across the two ends of a conductor is 1 volt and the current through it is 1 ampere.
Let us now look at one practical numerical example, how to use the Ohm's law.
How much current will an electric heater draw from a 220 volt line if the resistance of the heater coil is 50 ohms? Solution. V is equal to 220 volt. R is equal to 50 ohms. Therefore, using Ohm's law, I is equal to V upon R. That is equal to 220 divided by 50, which gives 4.4 ampere.
This numerical example therefore helps us in knowing how large or small the current will be for a given resistance and the applied voltage. In practical circuits, it is required many times either to increase the electric current or to decrease the electric current. If the applied voltage is kept fixed as we have at 220 volts, the resistance can be changed. For this, we need to know the properties of the resistance of a conducting wire.
To study the factors on which the resistance of a conductor depends. Materials required are a cell, an emitter, nichrome wires of different lengths, nichrome wires of different cross-section, a copper wire of same cross-section and same length, and a key. First, we will conduct the experiment using wires of different lengths. We connect the circuit. Now, plug the key and note the current in the emitter. Now replace the nichrome wire by another nichrome wire of different length and again note the emitter reading. Observations. It is observed that the emitter reading is different for different length. Now, we will conduct the experiment using wires of different cross-section area. We now replace the nichrome wire by a thicker nichrome wire of the same length and note down the current through the circuit. Observations. The emitter reading is increased when a thicker wire of the same material and the same length is used. Dependence on the material of the conductor. Now replace the nichrome wire by a copper wire of the same length and same area of cross-section as that of the nichrome wire and note down the current through the circuit. A change in the emitter reading is observed when a wire of different material of the same length and same area of cross-section is used. Conclusions. When the length of the wire is doubled, the emitter reading decreases to 1/2. The emitter reading is increased when thicker wire of the same material and the same length is used. A change in the emitter reading is observed when a wire of different material of the same length and the same area of cross-section is used.
Series of experiments performed have shown that the resistance of a conducting wire depends upon its length, area of cross-section and the nature of the material. So, we now combine these three factors and write it in the form of an equation. R, the resistance, is found to be directly proportional to the length, inversely proportional to the cross-sectional area. Combining these two equations, we therefore get R proportional to L by A, or R is equal to rho L by A.
The constant of proportionality rho is called the electrical resistivity of the material of the conductor. The metals and alloys have very low resistivity. The insulators, on the other hand, have very high resistivity. The semiconductors have resistivity in between that of insulators and conductors. In a nutshell, we have seen how the current through a conductor depends upon its resistance and the potential difference across its ends.
In various electrical gadgets, resistors are often connected in combinations. There are two popular combinations: resistances in series. When the resistances are joined end to end, such a combination of resistances is known as resistances in series.
Let us now understand what happens to the value of current when number of resistances are connected in series in a circuit. To study the effect on the magnitude of current and voltage, when many resistors are connected in series in a circuit. Apparatus required are 3 resistances of different values, a battery, an emitter, a plug key, connecting wires, and a voltmeter. Effect on the magnitude of current. Connect the circuit, plug the key, and note the emitter reading. Change the position of emitter to anywhere in between the resistors and note the emitter reading each time. Effect on the magnitude of voltage. Connect the circuit. Insert a voltmeter across the ends X and Y. Plug the key and note the voltmeter reading. Now, insert the voltmeter across the ends of each resistor successively. Plug the key and note the voltmeter reading each time. Observations. It is observed that the current in the emitter is the same independent of its position in the electric circuit. The potential difference in the voltmeter is different across each resistance. Conclusions. Thus, in a series combination of resistances, the current is the same in every part of the circuit, and the total potential difference across the combination of resistances in series is equal to the sum of potential difference across the individual resistors.
On the other hand, when the resistors are connected between the two endpoints A and B as shown in the figure, the resistances are said to be in parallel combination.
Let us now understand what happens to the value of the current when the resistances are connected in parallel by performing a simple activity. To study the behavior of 3 resistors joined in parallel in an electric circuit, apparatus required are 3 resistances of different values, a voltmeter, an emitter, a plug key, a battery, and connecting wires. Connect the circuit as shown. Plug the key and note the emitter reading and voltmeter reading. Now, successively insert the emitter in series and voltmeter across each resistance. Note the emitter reading and voltmeter reading each time. Observations. The potential difference in voltmeter across each resistor is constant. The current in the emitter through each resistance is different. Conclusions. Thus, in parallel combination of resistances, the voltage remains constant and the total current is the sum of the separate currents through each branch of the combination. Application of the Ohm's law to the combination of resistances.
So now we have seen that resistances can be connected either in series or they can be connected in parallel. But what is the equivalent resistance of such a combination in an electric circuit? This can be calculated by using the Ohm's law.
In the electric circuit, let I be the current through the circuit. As we already know, the current through each resistor is also I. Now, we replace the three resistors by an equivalent single resistor R. And the current is same, I. Applying Ohm's law to the equivalent circuit, V is equal to IR. On applying Ohm's law to the three resistors separately, V1 is equal to IR1, V2 is equal to IR2, and V3 is equal to IR3. But we know V is equal to V1 plus V2 plus V3. From equations, IR is equal to IR1 plus IR2 plus IR3, or R is equal to R1 plus R2 plus R3. Conclusion. We now conclude that when several resistances are joined in series, the resistance of the combination equals the sum of their individual resistances. Resistances in parallel. In the electric circuit shown here, the voltage drop across each resistor is equal to the voltage of the battery, but the current gets divided into three branches. The sum of all currents gives the total current through the circuit, that is, I is equal to I1 plus I2 plus I3. Let Rp be the equivalent resistance of the parallel combination of resistors. By applying Ohm's law, let Rp be the equivalent resistance of the parallel combination of resistors. By applying Ohm's law, I is equal to V upon Rp. On applying Ohm's law to each resistor, I1 is equal to V upon R1. I2 is equal to V upon R2. And I3 is equal to V upon R3. Now, I is equal to I1 plus I2 plus I3. On substituting values, we get V upon Rp is equal to V upon R1 plus V upon R2 plus V upon R3, or 1 upon Rp is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Thus, we may conclude that the reciprocal of the equivalent resistance of a group of resistances joined in parallel is equal to the sum of the reciprocals of individual resistances.
Lastly, let us now look at the advantages and the disadvantages of series and parallel combination of resistances.
In a series connection, there is more power loss because the source voltage gets divided among the resistances. For example, in a line of 230 volt, if two lamps are joined in series, each will get only 115 volt and the lamps will glow very dimly. On the other hand, in a parallel connection, the power loss is less and the resistances receive the same voltage, and so no lamp will glow dim. In a series connection, when one lamp blows out, the entire circuit breaks as no current flows. However, in a parallel connection, the circuit path of other appliances is not disturbed. Because of the above reasons, household circuits are always connected in parallel. Recap. In our discussions today, we have learnt the Ohm's law. The resistance of a conductor depends on its length, its cross-sectional area, and the material of which the conductor is made. The resistances are commonly connected either in series or in parallel. The equivalent resistance of several resistors in series is the sum of their separate resistances. That is, R is equal to R1 plus R2 plus R3. For a set of resistances connected in parallel, have an equivalent resistance given by 1 upon R is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 and so on.
So dear children, let us meet next time. Goodbye till then.